It has the world's largest high-speed rail network that connects hundreds of cities, as well as a huge air transport system with 227 airports.
China has flattened over 400 mountains to build massive airports in places where planes were never supposed to land. Valleys were filled, ridges removed, and entire landscapes reshaped to create flat runways in the sky. How did they move millions of cubic meters of earth so fast? Could you imagine landing on a cliff edge, manufacturing flat earth? In a vertical country, western and southwestern China are not flat lands. They are steep, broken, and uneven. In many parts of this region, more than 2/3 of the land is covered by mountains, high ridges, and deep valleys. Large areas sit on limestone rock that forms sharp peaks, sinkholes, and underground caves. This type of land is called karst terrain. It is beautiful, but it is very difficult to build on. 3 major regions show this clearly: Sichuan Province, Guangxi Zhuang Autonomous Region, and Chongqing. In these areas, mountains stretch across the horizon. Valleys cut deeply into the ground. Flat land is rare and often too small for large projects. Finding a single piece of level ground bigger than 3 to 5 square kilometers can be extremely difficult. Modern airports cannot sit on narrow or uneven land. A runway must be long, straight, and stable. The ground must not shift or sink. Aircraft need wide turning areas and strong foundations. Traditional airport construction depends on large natural plains. In southwestern China, those plains simply do not exist in many counties. Before the expansion of air travel, many communities in these regions were isolated. A trip to a major city could take 4 to 6 hours by car. Roads twisted through mountains and passed along steep cliffs. During heavy rain or fog, travel became even slower. Transporting goods was costly and unpredictable. Fresh food, medical supplies, and industrial equipment took longer to arrive. Emergency services faced serious delays. In some remote counties, reaching advanced hospitals required long road journeys. This created pressure on local health systems. Tourism also suffered. The region is rich in natural beauty, including rivers, forests, and dramatic stone landscapes. However, without fast access, visitor numbers remained low compared to eastern China. Between 2015 and 2020, China increased investment in civil aviation across western regions. The goal was not only transportation, it was also an economic balance. The country wanted to connect inland provinces more directly with national markets. Rather than moving large populations away from mountains, the strategy focused on bringing infrastructure into the mountains. This created a major decision. Most countries design projects to fit the natural landscape. Engineers adjust runways, shorten facilities, or choose different locations. In parts of southwestern China, that option was limited. The terrain left little room for compromise. China adopted a different engineering approach. Instead of building around mountains, construction teams began removing them. Instead of searching endlessly for flat land, they created it. Hilltops were cut down. Valleys were filled with rock and soil. Entire ridgelines were reshaped into wide, level platforms. These platforms were engineered to meet strict aviation safety standards. This shift marked a new stage in infrastructure development. Geography was no longer treated as an unchangeable barrier. It became a challenge to be redesigned with machinery, planning, and large-scale coordination. If geography was the problem, how far was China willing to go to eliminate it? The answer begins with a project so massive it erased nearly 370 mountains in one single location. The 370 mountains. Inside Chengdu Tianfu's land. Transformation Chengdu Tianfu International Airport is one of the most impressive engineering projects in southwestern China. It is located in Jinchengjiang, about 50 kilometers southeast of Chengdu City. The area where the airport stands was originally rolling hills, ranging from 500 to 700 meters in elevation. No naturally flat area existed that could support an international airport. Engineers had to create a level platform from scratch to meet aviation safety standards. The scale of the project is enormous. Approximately 370 hills were completely flattened to make room for the airport. More than 230 million cubic meters of earth and rock were moved during the construction. To imagine this, it is roughly the volume of tens of thousands of Olympic swimming pools, or several times the volume of the largest ancient pyramids in the world. Every mountain was carefully analyzed before being cut to ensure structural stability. Blasting operations were the main method used to remove the hills. Tens of millions of kilograms of explosives were deployed in carefully timed sequences. Each detonation followed precise planning using three-dimensional geological models to predict how the rock would fall and minimize risk. Seismic monitoring systems were placed around the construction site to protect nearby communities from unintended vibrations. Engineers used this approach to balance speed, safety, and accuracy. Once the hills were removed, 6 major valleys were filled to create a flat foundation. Some of these valleys were over 100 meters deep. The fill material was compacted in layers, and the level of the foundation was controlled within centimeters to ensure runway stability. This allowed the airport to meet all international standards for large aircraft operations. The workforce and machinery deployed were massive. Over 20,000 workers were involved, supported by thousands of excavators, dump trucks, and drilling rigs. The first phase of construction was completed in under 4 years, demonstrating the project's efficiency given its size. Engineers worked around the clock to meet deadlines without compromising safety. Structural stabilization was another critical aspect. Thousands of deep concrete piles were installed to support the massive weight of the runways and terminals. Layers of compacted soil further stabilized the ground. Advanced drainage networks were built beneath the runway to prevent water accumulation and soil weakening, ensuring the airport remains safe under heavy rain or snow. This project shows how engineering can transform an entire landscape. Mountains were removed, valleys were filled, and flat land was created where none existed naturally. Every detail, from excavation to compaction, was calculated to guarantee a safe and functional airport. The runway. On the edge, Hechi Jinchengjiang Airport. Hechi Jinchengjiang Airport is built in one of China's most challenging terrains. The surrounding area consists of limestone peaks, underground caves, and tightly packed hills, forming a karst landscape. This made construction difficult because the ground is naturally unstable, and large areas of flat land simply do not exist. Engineers had to reshape the mountains and valleys while maintaining the stability of the land. About 65 hilltops were cut down to make space for the airport. Around 13 million cubic meters of earth and rock were moved to fill valleys and level the terrain. Each hill and valley had to be studied carefully because the limestone bedrock contains underground channels and cavities that could collapse if disturbed improperly. Precision planning ensured that every section of the runway was supported by solid foundations. The runway itself is approximately 2,200 meters long. It sits on a plateau with steep drops reaching 300 meters on both sides. The construction created a flat corridor in a place that was once a sharp ridge. Pilots landing here described the experience as similar to landing on a moving platform, suspended in a sea of mountains. The margin for error is small, requiring both careful planning and advanced technology. Wind and weather added another layer of complexity. The region is prone to strong wind shear and dense fog for much of the year. Visibility can drop below 1 kilometer regularly, making navigation challenging. The airport was equipped with precision landing systems and advanced guidance technology to ensure aircraft can land safely even under difficult weather conditions. Operationally, the airport handles modest passenger numbers, but its impact on the region is significant. Travel time by air from nearby cities has been reduced from around 5 hours by road to only 1 hour. This has allowed more efficient transport of goods and people, directly connecting isolated communities with major economic centers. The economic effects have been noticeable. The regional GDP increased after the airport opened, providing new business opportunities. Poverty levels fell in some counties, and tourism saw significant growth. The airport has made previously hard-to-reach scenic areas accessible to visitors, boosting the local economy and providing new employment opportunities. Hechi Jinchengjiang Airport demonstrates how precision engineering can overcome extreme geographical challenges. By carefully reshaping the landscape, constructing stable foundations, and installing advanced navigation technology, China created a functional airport in a place previously considered impossible. If one runway balanced on cliffs feels extreme, what about an airport built above the clouds, where fog dominates more than half the year? The airport in the clouds, Wanzhou Wuqiao Airport. Wanzhou Wuqiao Airport is one of the highest airports in southwestern China. It sits over 1,700 meters above sea level, making construction extremely challenging. The site faces harsh winter temperatures, heavy ice accumulation, and strong winds that can exceed 50 meters per second. These conditions demanded careful planning to maintain safety for both construction workers and future passengers. To create a flat platform, engineers flattened 7 major mountains, including Taohua Mountain. Entire ridgelines were reshaped and valleys were filled to provide a stable foundation for the runway. The project required precise calculation to ensure that the large volumes of earth and rock would settle evenly and remain stable under heavy aircraft traffic. The area contains numerous karst caves, over 40 in total, which posed a serious risk for structural collapse. Engineers reinforced these underground spaces by installing deep concrete columns that reach into the bedrock. Additional geological stabilization methods, including rock anchors and layered compaction, were used to secure the foundation and prevent long-term settlement. Weather plays a major role in airport operations. Fog covers the region for a large portion of the year, often reducing visibility to less than 1 kilometer. To address this, advanced automatic landing systems were installed, allowing aircraft to land safely even in near-zero visibility conditions. Strong winds combined with fog make each landing a careful exercise in precision. The airport has had a significant effect on the local economy. It supports tourism in the Three Gorges area, making scenic regions more accessible to visitors. Local businesses have grown, and travel time from remote areas to Chongqing City has been drastically reduced. This has boosted economic activity in northeastern districts and created opportunities for thousands of residents. Wanzhou Wuqiao Airport shows how human engineering can reshape extreme landscapes. Mountains were cut, ridges leveled, and underground spaces reinforced to create a stable, functional airport in a region once considered inaccessible. The project required advanced technology, careful planning, and thousands of workers to complete successfully. These 3 airports alone required the removal of more than 440 mountains. But how exactly were these mountains cut down so precisely without causing regional disasters? The engineering systems behind the destruction removing mountains on such a massive scale required more than brute force. Engineers relied on advanced systems to make the work safe, accurate, and efficient. Every step was planned to prevent accidents, structural failures, and environmental damage. Digital terrain mapping was the foundation of the operation. High-resolution satellite imagery, 3-dimensional laser scanning, and geographic information system modeling allowed engineers to understand the exact shape of each mountain and valley. These tools helped determine where to place explosives and how to distribute fill material. Every hilltop and cavity was analyzed in detail before construction began. Controlled blasting sequences were used to remove the mountain safely. Millisecond-time detonators broke the rock in a precise order, minimizing the risk of uncontrolled collapses. Engineers carefully calculated the direction of rock fragmentation to ensure that debris did not fall into neighboring areas or damage surrounding hills. This approach allowed the mountains to be dismantled efficiently while protecting nearby communities. Excavated material was reused as valley fill, reducing construction waste. Rocks were layered and compacted in stages to create strong foundations. This recycling not only made the project more sustainable, but also helped balance the massive volumes of earth moved. Without these methods, stabilizing the airport platforms would have been nearly impossible. Deep foundation engineering was critical to prevent subsidence. Concrete piles were driven 20 to 30 meters into unstable soil. In karst regions, cement was injected into underground voids to fill gaps and strengthen the ground. Sensors were embedded to monitor long-term settlement, ensuring that the runways remain level and safe for decades. Smart runway technology further enhanced safety and efficiency. Embedded sensors monitor stress in real time, providing data on vibrations, weight distribution, and potential weaknesses. These systems also optimize aircraft taxiing and fuel usage, reducing both operating costs and environmental impact. Together, these engineering systems allowed China to flatten hundreds of mountains without endangering workers or surrounding communities. Technology turned what seemed impossible into a precise, controlled operation. But while the engineering appears flawless on the surface, what happened to the environment and the people living near these disappearing mountains? Environmental and geological consequences. Flattening hundreds of mountains and filling deep valleys has effects beyond construction. The land, water, air, and nearby communities all face changes. Understanding these impacts was critical for the success of airports like Chengdu Tianfu, Hechi Jinchengjiang, and Wanzhou Wuqiao. Engineers and planners had to consider soil, water, vegetation, air quality, and human settlements to prevent disasters. One major concern was soil erosion. Removing mountain peaks and topsoil exposes Earth to wind and rain. Steep slopes created by blasting can shed sediment into nearby rivers, causing siltation and changing river flow patterns. To manage this, slope stabilization programs were implemented. Engineers reinforced slopes with layered earth, concrete barriers, and retaining structures. Vegetation was replanted on exposed surfaces to hold soil and reduce erosion. Without these measures, heavy rain could have washed away parts of the newly created platforms, destabilizing runways and valley fills. Landslides posed another risk. Exposed rock and soil from blasting could easily slide under heavy rainfall. To prevent this, retaining walls were built along the edges of critical slopes. Terracing techniques were applied to reduce the angle of exposed surfaces, and fast-growing plants were planted to anchor the soil. In some areas, monitoring systems with sensors detect movement and vibrations, allowing early warnings in case of instability. These systems protect both the infrastructure and nearby communities. Water tables and underground karst systems were highly affected. Southwest China has limestone caves and channels that can collapse if disturbed. Filling cavities with concrete columns and grout helped stabilize these formations. Engineers also monitored groundwater levels to prevent sudden drops or flooding caused by disrupted flow. Maintaining the water table is essential for both ecosystem balance and long-term structural stability of airport foundations. Dust and air quality were also major concerns during construction. Blasting produces clouds of dust, which can affect workers and nearby villages. Water spray systems were installed to suppress airborne particles. Protective equipment, including respirators, was provided to workers, and construction schedules were adjusted during high wind periods to reduce the spread of dust. These measures helped maintain safer air conditions for both humans and wildlife. Noise and the displacement of communities were significant social issues. Explosives and heavy machinery produced intense noise over long periods. Some residents were temporarily relocated during blasting phases. Compensation programs were established to support displaced families, and infrastructure such as roads, schools, and housing was rebuilt or improved. This social management was essential to prevent conflicts and maintain local support for these massive projects. Long-term ecological mitigation was incorporated into the planning. Reforestation initiatives were launched on previously removed mountain slopes. Artificial wetlands were created near airport grounds to filter runoff and provide habitats for wildlife. Drainage and filtration systems were carefully designed to prevent polluted water from entering rivers. These measures aim to restore ecosystems gradually and maintain environmental balance after large-scale human intervention. Flattening mountains at this scale required not just engineering, but environmental strategy. Soil, water, air, and human life were all carefully managed to reduce risks. Without these interventions, the destruction of hundreds of mountains could have caused landslides, flooding, and lasting damage to local ecosystems. With mountains removed, valleys filled, and ecosystems altered, what scale of national coordination was required to manage projects of this magnitude? National coordination, scale, and strategic expansion. China's large-scale mountain removal projects required far more than local engineering. They were part of a coordinated national plan driven by the Civil Aviation Administration of China. Between 2015 and 2020, detailed planning cycles were executed to identify areas where new airports could have the greatest impact. The goal was to integrate air transportation into the Western development strategy, connecting remote provinces to national and international markets while supporting economic growth in historically isolated regions. The financial scale of these projects was immense. At tens of billions of US dollars were invested in airport construction, infrastructure upgrades, and related logistics. Investments were not isolated. Regional clusters of airports were developed to create interconnected networks. This allowed aircraft to move efficiently between cities and regions, while also creating redundancies to improve reliability. Funding covered everything from terrain modeling and blasting operations to underground stabilization and high-tech runway systems. Integration with urban planning was another key factor. Each airport was not just a landing strip. It became the center of economic zones. Logistics hubs were planned to facilitate the movement of goods, reduce transportation times, and encourage industrial development near the airports. In some cases, new roads, bridges, and residential areas were constructed to support the anticipated population, growth, and commercial activity. Population distribution effects were carefully considered to avoid overconcentration, while still making remote areas accessible. Military and civil infrastructure often shared design standards. Runways were built to accommodate both commercial and strategic aircraft. The location of these airports allowed rapid deployment in emergencies and ensured that regions with complex terrain could be accessed quickly if needed. Shared standards and dual-use design did not compromise civilian safety or efficiency. This careful planning reflects a long-term strategic vision that aligns with both national defense and civilian transportation needs. The cumulative numbers are staggering. Across the three major projects, more than 440 mountains were leveled. Hundreds of millions of cubic meters of earth and rock were moved, filling dozens of valleys to create stable, level foundations. Thousands of workers and heavy machines were deployed simultaneously, with precision blasting, foundation reinforcement, and slope stabilization applied consistently across all sites. The coordination of these activities required synchronized timelines, advanced monitoring, and continuous adjustments to manage both natural and human variables. When compared to global engineering projects, the scale and speed are exceptional. Other countries have built airports on artificial islands or through extensive tunneling systems, but China's mountain flattening projects combine multiple challenges: high elevations, extreme weather, karst geology, and massive earth displacement. The intensity of operations, speed of construction, and the number of simultaneous engineering interventions surpass most international examples. These projects transformed entire regions in a fraction of the time usually required for similar global undertakings. The next phase: China's expanding aviation network. China's aviation expansion shows no signs of slowing. Beyond Chengdu Tianfu, Hechi Jinchengjiang, and Wanzhou Wuqiao, planners are targeting additional remote regions in western and southwestern provinces. The goal is to improve accessibility, support local economies, and integrate more isolated counties into national and international networks. Areas in Yunnan, Guizhou, and Tibet are prime candidates due to their high mountains, deep valleys, and limited infrastructure. The next phase focuses on scaling the techniques used in earlier projects. Engineers are applying lessons learned from previous mountain removal operations, such as optimized blasting sequences, reinforced karst stabilization, and advanced drainage systems. Technology is being upgraded with more precise GIS mapping, real-time slope monitoring, and high-capacity automated earth-moving machinery. These tools allow construction to proceed faster while maintaining safety for workers and nearby communities. Financial investment continues to grow. Multi-billion-dollar budgets are being allocated to both new airports and the improvement of existing regional air hubs. Funding covers not only the construction of runways, but also urban planning integration, logistics centers, and transportation corridors, connecting air hubs to surrounding towns. This ensures that airports are not isolated points, but central nodes in regional development networks. Environmental and social considerations remain a core component. Reforestation, artificial wetlands, and runoff filtration are applied proactively to limit ecological impact. Community relocation is carefully managed, with compensation programs and infrastructure upgrades for affected villages. Air quality control and dust suppression systems are standard in every new project to protect both workers and residents. Engineers also monitor groundwater and karst cave systems to prevent long-term geological instability. The scale of human and machine mobilization is extraordinary. Thousands of workers, hundreds of excavators, and millions of cubic meters of earth continue to be moved in each project. Each new site requires hundreds of safety sensors, retaining walls, and slope stabilization measures to maintain both operational and environmental safety. Coordination between civil authorities, construction companies, and local governments ensures that these operations run smoothly across vast regions with difficult terrain. Strategically, these airports serve more than transportation. Many are positioned to support emergency response, military logistics, and rapid deployment capabilities while still functioning as commercial hubs. This dual-use philosophy maximizes the efficiency of infrastructure investments and strengthens national resilience in high-altitude and remote areas. By combining engineering innovation, environmental planning, and national coordination, China is creating one of the most extensive aviation networks in the world. Each new project not only connects people but reshapes landscapes, turning mountains into platforms capable of supporting economic, social, and strategic objectives. Hundreds of mountains have already been leveled, valleys filled, and skies connected. As this network expands, one question remains. How many more impossible landscapes will China turn into hubs of travel, trade, and transformation next?